I wonder what the relationship between kinetic energy and height is from a basketball. We will be creating a ramp at differing heights. Then, we will roll a tennis ball off the ramp and measure the final velocity to test the relationship between the height of a ramp and the velocity, using the energy conservation principle. The independent variable will be the height of the ramp, and the dependent variable will be the final velocity of the tennis ball. For our experimental setup, we will have a ramp set up at 6 inches. We will then measure the final velocity and the final rotational speed of the tennis ball just as it leaves the ramp using a ruler and a slow motion camera setup. For our procedure, we will have our ramp height first set at 6 inches and we will increment up by 6 inches until we reach 2 feet. We will measure the velocity and rotational speed of the ball by recording in slow motion and then using the displacement over time formula over a time interval of 4 frames, which is roughly 1/15 of a second. We use a short time interval to mitigate friction's effect on the ball, thus giving us accurate results. We will have 3 trials at each ramp height to mitigate error. Here is our first trial for the 6-inch height. Here is the first trial for the 12-inch height, aka 1 foot. Here is the trial for the 18-inch height. Here is the trial for the 24-inch or 2 feet height. To record my data, I went through the slow-mo footage and paused after 4 frames and then did the displacement over time formula. Then I had to convert the units into feet per second. Here is the dimensional analysis. Here is the 6-inch data table. We repeated this dimensional analysis for each angular velocity and translational velocity data point that you can see in the data tables. Here is the 12-inch data table. Here is the 18-inch data table. Here is the 24-inch data table. For our translational velocity graph, the y-axis was height in feet, and the x-axis was translational velocity in feet per second. There seemed to be a fairly linear relationship, but according to our derivation, the height is proportional to the square of the velocity, or velocity squared. When we graphed the height against velocity squared, we got a better linear fit. For our rotational velocity graph, the y-axis was height in feet, and the x-axis was rotational velocity in radians per second. There seemed to be a fairly linear relationship, but according to our derivation, the height is proportional to rotational velocity squared. However, when we graphed the height against the rotational velocity squared, we got a worse linear fit. This was due to the high percent error in our experiment. Speaking of percent error, here are our percent error calculations. The expected value is generated from the gravitational potential energy, and the value we got from the experiment is the combination of the rotational and translational kinetic energies. We then compare the two values using the percent error formula to get our percent error. Here is our percent error for 6 inches. Here is our percent error for 12 inches. Here is our percent error for 18 inches. here is our percent error for 24 inches. Some reasons for sources of error include that whenever the tennis ball rolled off the ramp and onto the carpet, the tennis ball bounced back up. It is more noticeable when the ramp height is higher. This bounce releases energy, making the experiment move away from the perfect conservation of energy condition we wanted it to be in. Another form of error is that when we reviewed the slow motion footage, the 240 FPS footage had 3 frames where the tennis ball did not move, and then the next frame skipped ahead. So we had to use the regular 60 FPS footage, and even then there was a little bit of glitching here and there. This encoding error made it more difficult to discern the true velocity and rotational velocity from the recording. We could have made our experimental design better by having smaller heights. So when the height of the ramp was 18 and 24 inches, the tennis ball was moving at such a speed and there was such an angle between the ground and the ramp that the ball moved incredibly fast, and when it reached the ground, it bounced up into the air. If we had started at 4 inches and incremented up by 3 inches until we reached 13 inches, then the tennis ball wouldn't have been as fast, and the angle between the ground and the ramp wouldn't have been as steep, so the tennis ball wouldn't have bounced as much. Since we could only use household objects, and I didn't have a meter stick, the units had to be in feet. If we were at school, we could have done this exact experiment, but instead of a tennis ball, we could have used a marble, and we could have used the velocity reader mechanism to more accurately figure out the velocity. Height is proportional to velocity squared and to omega, or rotational velocity squared.